welcome. Yes.
And then this.
And here to follow the next slide.
Okay, so that's two, I think. Yeah, thanks. So thanks for the kind introduction. Yeah, this is the first time I saw the makeout change, so I single-handedly bring down the height of all the speaker. Yeah, so Dorian already talked about the challenge setup, so I would like to offer my perspective as a participant. So I joined the challenge for around 2 months, so March and April this year, basically. And the task is straightforward. It's basically, can I go back? Oh, here. An image-to-image translation test, where given a bright field or any kind of transmitted light images, you are asked to predict 4 channels for every field of view. And there's a lot of obvious reason why we want to go label-free. Besides the reduced cytotoxicity and other reason, we can free up some fluorescent channels to pursue other targets. And also we can go to live cell imaging direction, where actually you can gather way more temporal information of the cell state that might be arguably much more deterministic of the system that we are studying. This one. So this task is actually not new. There has been efforts in paper, at least in the last 6, I think 10 years, trying to virtual stain from transmitted light images. But I think that this challenge still offers some novelty in the sense that this is maybe the most heterogeneous data set with gathering like 30 different studies and different magnification, depth of focus, etc., different cell type and morphologies. So because of this relatively large and diverse data set, there's offer a chance to generalize solution. So from the distribution of the data, training data set that were offered to us in log scale, you can see obviously that actin is 1/10 of the data for nucleus, which means that you have very much reduced capacity to model anything for actin. So there's a great class imbalance. And you can see here also that there are different combinations for each field of view or each study in specific, which mean that there are many incomplete organelle to organelle and organelle to transmitted light joint distribution to model. But according to, through my other PhD kind of studies, we learned that organelle to organelle relationship are quite robust within unperturbed population. So I wanted to investigate that can these missing joint distribution be modeled based on this very incomplete like joint distribution sets. So that brings me to my failed attempt, actually. That basically the idea is that I embedded the transmitted light to a latent vector, and through the and also do the same for the organelle channel, and through the diffusion process and organelle token conditioning generation, so reverse diffusion with token conditioning. I learned the mapping between the transmitted light image and the organelle distribution. And actually, as a preface, is not performing that well. It's actually the model failed to interpolate beyond the channel combination that is provided in the training set. So we lack enough data for this task in this challenge. However, this approach actually worked on another data set with complete joint distribution. And yeah, please feel free to ask me about it later if you're interested. So with time was running out, I default to a much simpler solution, which is one model for each organelle, so an organelle-specific VQGAN. So it's basically an autoencoder with an encoder, and a decoder in this case acted as a generator that learn the mapping between transmitted light and then the organelle of interest. And then a discriminator here that is forcing the generator to generate a more perceptually realistic image. And then we also have a quantizer in the middle that map the continuous embedding to a discrete one. And then the model size end up to be around 50 million parameter, and this is considered right now relatively light for deep learning. These models have become so large these days. Yeah, and this is what I have in my validation set. You can see that for most of the combination that I see, when I split like random validation and training, then my output looks pretty much close to the ground truth. So we were able to model most of the combination between transmitted line modality and channel, organelle channel. This one. So the conclusion is for modeling is that a simpler method actually works better in this setup. And I learned that modeling multi-organelle in this case require a lot more joint distribution information, and latent diffusion is very data hungry. And also when training the VQGAN, I noticed that like the organelle with lower sample will require much more training tips and tricks than those with sufficient sample. Then you just let it run, basically. And then, yeah, scientifically, maybe we establish the current performance of the label-free model on these 4 organelle channel. And there's actually one question that I want to ask you as like experimentalists, biologists. At what point, like what kind of confirmation or confidence do you have to use this model? So when do you use this model, and how do you use the model? How do you imagine incorporating this actually in your research? Yeah, so I look forward to any discussion today or tomorrow about these. Thank you.